All right. Thank you, and thanks to the California Water Quality Monitoring Collaboration Network. Glad to be here and to wrap up your webinar series. As Eric mentioned, my name is Ryan Searcy, and I am the Water Quality Modeler at Heal the Bay. Heal the Bay is a Santa Monica-based nonprofit dedicated to keeping the Bay and its watersheds safe, healthy, and clean for all those that would. Okay. As I mentioned, I work for Heal the Bay. Heal the Bay, many of you may be familiar with us with our Beach Report Card program, in which we create weekly grades for near 500 beaches across the state, making an easily understandable scale for beachgoers to check water quality at their favorite beach. But what I want to talk to you about today is a new tool that we have been developing, as Eric mentioned, in collaboration with Stanford and UCLA and funded by the State Water Resources Control Board, and that's the NowCast program. And so I want to talk about how we can predict water quality and protect beachgoer health. So let's start with a little motivation about why we would want to do this. Well, we all know that water quality is very important. It has implications in not only our health, but our coastal economies. And we know that when people go into contaminated water, that they get sick. And even the most recent EPI studies done around the state verify that, essentially saying that as fecal indicator bacteria or organisms that are indicative of pathogens increase in our water bodies, so does our risk of actually getting sick. And so the question now becomes, how do we know how much bacteria is in the water? And in short, we really don't have that great of an idea at this moment. And there's a couple issues. The first is that most beaches around the state and around the world are only monitored once weekly. In California, only 5% of those 500 beaches I mentioned are sampled more than once a week. So beachgoers are left with a sparse set of information to make decisions on. Additionally, those samples that are taken typically take 24 to 48 hours to come back from the lab and be made public. And as we know, water quality changes on a much shorter time scale than this. It changes day to day and even hour to hour. And so when that information comes back, it's old. And so now beachgoers have old data and only a little bit of it, which is unacceptable, really. And so what's really needed is a better public notification tool, one that communicates risk accurately and often and is easily understandable by beachgoers and easily accessible. And so the NowCast system provides beachgoers daily water quality predictions for beaches across the state. These predictions are made by statistical models that are calibrated on years of bacterial and environmental data. And these models are unique to each beach and can be more accurate than relying on the current method, which is relying on the most recent sample to post the beach. And these predictions are easily accessible. They can be found on our Beach Report Card platform, on our website, and our mobile app. And so beachgoers can log on, find the beach they're interested in, check their water quality, the NowCast prediction, and make the decision on where to go. So a bit of background on our NowCast system, starting with predictive modeling. Many of you may know it by the more sexy name of machine learning, and that's used pretty much everywhere these days, right? It's used in the facial recognition software that is behind the selfies that we take. It's used on our ETAs when we search for directions on Google Maps. It's how we're advertised to, but it's also been used to predict water quality. And our program certainly isn't the first or only one to be researching and implementing programs like this. Countries like Ireland, Hong Kong, Germany, Croatia, New Zealand, and the Great Lakes and Puerto Rico have also explored programs like this. But our program, our NowCast system in California, is the first time, as far as I know, that this has been done at such scale, at such a unique state as California. And so our project got started initially as a research endeavor, again funded by the State Water Resources Control Board and in collaboration with Stanford and UCLA. And we started out asking, could we create predictive models that accurately predicted bacteria levels at the beach? And so we created over 700 different models at 25 different California beaches. And our results were published in 2 peer-reviewed works, essentially stating or concluding that indeed models can be created that are more accurate than the current method alone. Again, the current method being relying on the most recent sample to make a beach management decision. And not only are these models unique to each beach, they're unique to each FIB type and season. And so that was great. We found that this is a technically feasible endeavor, but we needed to research, could we actually implement this alongside existing monitoring and public notification programs? And so we held a pilot study in 2015 with 3 Southern California beach agencies, and we ran our models alongside of them daily between Memorial Day and Labor Day. And we found that our program integrates rather well. It's low cost. It provides daily information to beachgoers. It required very minimal changes to integrate into the monitoring programs. However, it was found that local managers would prefer a third party like Heal the Bay to run this along external to their programs due to available resources for those beach agencies. And so where we're at now is essentially implementing and expanding this program to more and more beaches and creating daily predictions every day of the season. So now let's look at the models themselves. We'll get into the weeds a little bit here. When I want to go and create a model for a certain beach and bacteria type, I start with a large data set, typically 8 to 10 years of bacterial and environmental data. And the bacteria sample data comes from our beach agency partners. So that's one key that we collaborate with them, is that we actually get the dependent variable of our models, what our models are actually trying to predict and what they're calibrated on. And then we also collect associated environmental data. This is data that is likely to be related to influencing bacteria levels. So environmental forcing mechanisms like tides, rainfall, meteorological conditions, wave parameters, and even stream flow if there's a stream or a river flowing into the beach. And so we compile all of this into a giant data set, and we use a large fraction of it to calibrate our models, and we set aside the remainder as a validation data set to make sure that our models are able to predict well on data that it has not seen or been trained on. And so we take our data sets and we employ certain machine learning algorithms to create our models. Currently, we use some of the most simple methods because they're the most easy to implement and understand, yet they seem to be producing the most accurate results. At least that's what we have found in our last 5 years of doing this program. And so multiple linear regression is probably the most common form of modeling. And that is a model that essentially predicts bacteria on a continuous spectrum as a function of environmental variables. So you can imagine the x-axis being an environmental variable like tide or waves. And for every unit increase or change in that variable, you see an associated change in the y-axis or the predicted bacteria concentration. But because beachgoers don't really care about the precise concentration of bacteria in the water, they really want to know, is it safe to swim or not? If our model, MLR model, predicts bacteria above a certain threshold, we say the prediction is for poor water quality. And vice versa. If it's below a certain threshold, we say that it's predicted to be good water quality today. The second type of model is binary logistic regression. It doesn't require a linear relationship to the variables as much as MLR models do. It's useful for clearly binary distributions of variables that are the beaches that are either squeaky clean or really high in bacteria and not very continuous on its distribution. And so the BLR model's output is the probability of an exceedance. And so if the probability is above 50%, then we say that the model has predicted poor water quality and vice versa. But again, these models are binary classifiers. That is, they predict good or poor water quality only. And so we're fortunate to be able to tune these models to be able to predict both good water quality and poor water quality as best as possible. So as we calibrate our models, we want to maximize the amount of true positives, that is the correctly predicted poor water quality condition days, and maximize the percentage of true negatives created or predicted, that is the number of correctly predicted good water quality days. And those two things are inversely related, as you can imagine. And so it becomes kind of a delicate balance on how we tune our models. I could create a model, conceivably, that always predicted water quality to be poor. And it would have 100% accuracy in predicting those poor days, but I would probably get a lot of angry phone calls from beach managers asking why my model always predicted poor water quality. So again, this involves kind of a balance on what we want our models to predict. How do we want our models to act? And so our program follows a specific set of criteria that our models must meet in order to be acceptable to use on a daily basis. And so the first thing that we're looking for is the specificity of our model. That is, how accurate is our model in predicting good water quality, or FID compliance, or no post days, depending on what agency you work for. Most beaches in the state, fortunately, are pretty clean, and so the current method of relying on an old sample does a pretty good job at predicting good water quality days because there are so many subsequent days of good water quality. And so we've worked with beach agencies to determine acceptable level for our models to perform at that predicts good water quality well enough without over-predicting too often. And so that level is 85%. And that changes depending on certain beach characteristics. But for the most part, our specificity level is set to at least 85%. Now, the statistic that a lot of us care about is how well does this model predict poor water quality days, the sensitivity of the model. And I should say in our initial research, we found that the current method of relying on the most recent sample only was able to predict poor days on average at 30% accuracy. That is, the current method's average sensitivity is 30%. However, many of the beaches are much lower than that, oftentimes 0% at predicting those poor days, which again motivates the need to have a program kind of like this. So our sensitivity criteria is set that our models must meet that average, but they also must be at least 10% better than the current method at that particular beach. So if you have a really dirty beach like Santa Monica Pier, where their sensitivity there for the current method is 50% because it exceeds so often, our models must at least predict 60% or higher of those postings for us to say, okay, this is a good model. And so after this, after we're able to tune a model on the data that we calibrated it on, we then go and test our models on our validation data set, the data that it hasn't seen, to basically verify how well does our model do on generalized data, on how can we expect our model to perform in the summer. And if it's able to meet the same criteria in validation, we say, okay, the model is ready to be used for the season. And so now we're able to start making predictions with our NowCast system, our ensemble of models. And so in our NowCast system are models that are all calibrated on years of environmental and bacterial data, which means that these predictions capture the central tendency of water quality based on the observed environmental conditions over the past 8 to 10 years. Compare that to a single sample that is taken, again, only typically once weekly and not available until 2 days after, and that's highly variable. So it's a much more robust, science-based bit of water quality information than what a single sample could actually tell us at the beach. And so we implement our models daily during the season. Our models run through an automated code that is run by me and other modelers automatically at 7 in the morning. And essentially the code obtains the environmental variables for the previous day. You know, what was the weather like yesterday? What were the waves yesterday? Plugs it into the models and delivers the predictions to our stakeholder agencies and posts it on our beach report card platform. Now the hallmark of this program, again, is that this information is available every single day of the season. So in 2017, we had 10 beaches in our system, and you can expect over the course of a full summer season, on average, about 30 samples are taken if you average a once weekly sample. So we expected 300 days of water quality information available for the beaches in our system. Our models were able to predict 1,850 days of water quality, much more than what the current method alone could have done. At Cal Beach, because only 26 samples were taken, we provided an additional 124 days of predictions beyond sampling. At Redondo, an additional 151 days beyond sampling. And at Doheny Beach, where Orange County was very prudent and would take samples every time we predicted poor water quality, we even had an additional 163 days of information available to beachgoers at Doheny. So really high value information available every single day. And so wrapping up, we have a lot that we want to accomplish with our program in the future. We have a new website and app that we plan to launch this Memorial Day that will make accessing water quality information easier than ever. Users will be able to download the app and set public personal notifications for the beaches that they care about. And so they'll get a ring in their pocket every time that their beach is able to, or is expected to have poor water quality, which makes this a very simple and useful tool when making a decision on where to go to the beach. Of course, we want to expand our system to more beaches. We're currently narrowing down our list of beaches to about 20 beaches for this summer, but we want to go beyond that. We'd like to potentially expand to the international level and even upgrade our models to higher order modeling algorithms and apply them at beaches where perhaps there's not a lot of data available, additionally creating a forecasting system. So there's a lot ahead for the NowCast program. And I'm going to leave it there. Hopefully didn't boggle your mind too much with wonky modeling talk, but I'd love to take some questions and talk about this a little bit further. Yeah, good question, Eric. So we had an internal pilot season for winter models. Because we're so lucky to be in California, lots of our beaches are still used year-round, especially by the surf and dive communities. So we targeted 5 Southern California beaches that were popular with surfers and divers, and seeing if we could implement our models on a daily basis, just like we do in the summertime. Now, there are some nuances in the winter, right? And I should mention the winter in California is defined legally as November through March, because that's our main or our average wet season. And so there's some nuanced differences than the summer, right? There's more wet weather, so there's a lot more. There are a lot more days where I have to collaborate with beach managers to make sure that I'm not releasing a prediction during a rain advisory or a sewage spill. those acute events are take precedent over our predictions, obviously, and so we would not release NowCast predictions in those situations. And so I'm actually currently evaluating the performance of those models, but the performance during dry weather, non-rain advisory days, looks to be pretty spot on how we calibrated our models, which is a good sign for using this in the winter in the future. That's right. In fact, there are predictive modeling efforts done at SCOOS, which is based out of Scripps Institution of Oceanography, that are currently doing this right now. And so they predict harmful algal blooms over an area and provide maps to those that would use it. Still, the Bay isn't currently considering integrating this into the program as of yet. We're still kind of focusing on the recreational bacteria side of things, but it's certainly something that we would love to collaborate with somebody on in the future. For the NowCast system? Yes, that's correct. SCOOS is just doing it off the Pacific coast. Yeah, so for our winter program, that's correct. We only release predictions during dry weather. And we've defined that as what most agencies use as periods where they're, I should say wet weather is typically defined as periods of rain greater than 0.1 inches that have lasted over the past 72 hours, right? So that 3-day rule of significant rainfall. And so we don't make predictions during those periods. We do actually have quite a bit of data available outside of those rain events to calibrate our models on, enough to create models that actually met those same criteria that I presented. Again, those were beaches we looked at in Southern California. So we are not in the most, we're in kind of the drier part of the state, right? So if this was something that we'd be expanding up to the northern part of the state, we may face a lack of data depending on where we are in the state. Source control methods. Okay, so as, okay, I think I understand what you're trying to say. So, exactly, yeah. Right, so, we've come across a couple of examples. Let me talk about those. We were able to create successful models internally for Pismo Pier. So Pismo Pier has recently undergone construction. So we thought, it might not be the best time to create a model for that sort of beach because the conditions there may have changed. Now, we also had an incident with Santa Monica Pier where I believe around 2010, some BMPs were put in effect to prevent seabirds from roosting under the pier. And we subsequently saw a couple years in a row of improved water quality. In 2009, in the summer, there were something like 60 fecal coliform exceedances out of 150 samples. So, almost every third sample came back hot. But in 2010 through 2013, we saw only levels of like 20 exceedances. So quite a big improvement in water quality. And because of that, including 2010 through 2013 data, actually tripped our models up. We weren't able to create models that were effective because of changing conditions there. Only when we removed data before 2013 were we able to actually create effective models. So the long-winded answer to your question is that we have to consider that every single time that we find out that there's been some sort of BMP put in place, and that is exactly why we try to run this program collaboratively with our beach agencies. We are currently done, our grant with the state is done March of next year. We're not going to be content quitting and packing up and not doing it anymore though, so fortunately we're able to explore other funding options to continue this program. So that's kind of the other part of the work that we're doing this year is how can we continue to keep the program going and expand it to more and more beaches. Well, I have tried to reach out to agencies where I want to get beaches going. So you can expect a call from me, but we typically work with the county or the city public health agencies, so like the Department of Environmental Health at various cities to do this. But we're also interested in working alongside chambers of commerce or like peer management groups at various hotspot beaches. So if there's a beach that seems interesting or that would be valuable near you that you don't currently see in the system, we'd love to work with stakeholders who are actually interested in the program and would find this valuable. Yeah, Catherine Pease is doing our river work, and she's currently looking to develop a similar program to the beach report card where something like a grade would be available for people to check their local watering hole. Predictive models have been used in freshwater. There's a lot of work being done at the Great Lakes, and in fact, agencies at the Great Lakes use only predictive modeling to post their beaches because of the inefficiencies of sampling. I think until we have a richer set of data on different river spots and we kind of get our river report card, quote unquote, up and running, and we're probably not going to be doing modeling there for quite a bit. Okay, it looks like another one came in from SD. So sorry that I missed the first part of the presentation that you might have talked about this, but can you clarify what criteria is used to select a beach for which NowCast is used? So I believe this is different than what is the performance criteria. It's actually how do we decide which beaches that we include into the program. And so there's a number of factors that we consider, right? There's how valuable this beach would be. That is, do people go to this beach? Is this a popular beach where a lot of people could benefit from this program? The second is how much participation are we able to get from our collaborative agencies, or how much interest, I should say. We don't want to step on existing programs' toes, so we don't want to just come in and start making predictions without the consent, really, of the appropriate agency. The availability of data. So some beaches we might not have a rich sample data set for. Some we have plenty of data for. The level of water quality. Some beaches are much easier to model than others just based on their level of water quality. Beaches that are really dirty maybe, or really clean, maybe a little bit trickier to actually get a significant performing model than other beaches. And along that note, beaches that we have working models for. So if typically what I'll do is I'll select 40 or 50 beaches that I am interested in that I think would be good choices, and I model them all together. And from those, I'll probably get 75% of them actually having models that could potentially work and that do pass our criteria.